Assalamualaikum. Let's see. Lecture number 42. We will start a new chapter, chapter 8, and that will be a last topic chapter for this course. That is principal stresses under given loading. What? So, in this lecture 42, we will discuss what will be the principal stresses in a beam. So, if you look at the beam, under transverse load, it has a bending moment as well as a shear stress. Shear force. So what will be the principal stresses in that case? And then we will discuss about design of transmission shaft that you already discussed in detail for your design of machine element course. And in the end, we will discuss stress under combined loadings. Okay. In chapter 1 and 2, we analyze the normal stress due to centric loads, right? And we already discussed the normal stress. Then we discuss the shearing stress distribution of the circular member due to twisting couple or torque in chapter 3. Chapter 4 we discuss normal stress caused by bending couple. And chapter 5 and 6 we evaluate shearing stress due to transverse load. And whereas chapter 5 we draw shear force and bending moment diagram. In chapter 7 we'll find and how we learn how to the component of stress are transformed by rotation of coordinate axis and how to find principal planes, principal stress, and maximum shearing stress at a point. And it can be a in plane or out of plane depending on the nature of stresses. Okay. For this chapter, we will learn how to determine stress in structural member or machine element due to combination of loads and how to find corresponding principal and maximum stresses. Means we have a machine member or structure on which we have a multiple loads are applied. So how to find the principal stresses and maximum shear stress in that case we will discuss in this chapter. Okay, now let's see. Let's start with the beam. For the beam, we know that the formula. Let's suppose we have this overhanging beam. So we know the formula that prismatic beam subject to transverse load. Sigma x is my over I, or maximum normal stress is mc over I. And in case of shear stress, tau xy is vq over it, negative sign just showing the direction, whereas the maximum shear stress is vq over it. And if you look at the distribution, stress distribution, for example, if you take at C, so at C the top will be under tension and bottom will be under compression, and there will be only normal stresses. There will be no shear stress at top and bottom surface. But in between, but at the central axis or neutral axis, we have only shear stress, maximum shear stress, where the normal stress will be 0. But in between top surface and middle surface, neutral axis, neutral surface, or bottom or neutral surface, the stress distribution we have a normal stress as well as shear stress. Now there is a possibility that the maximum principal stress or maximum shear stress lie over here instead of at top surface or at the neutral axis. So the principal stresses, if you look at, so if we talk about top surface, it will be there is no shear stress, so these are my principal stresses. But and at the neutral axis where we have maximum shear stress, so I have to rotate 45 degrees to find the principal stresses, and that we find the method discussed in chapter 7. But in between, the orientation will be different. By different orientation, we have maximum and minimum stresses. And the maximum now, can the maximum normal stress within cross section be larger than sigma m, that is mc over I? Yes, it can be larger. Now let's see. These are for the rectangular beam, and this is showing y by c ratio. Y is this distance, and C means Y over C ratio means we are talking about top surface or bottom surface, -1. And this is showing, and these values are showing the ratio between sigma max and sigma m, that is due to bending moment. Similarly over here, sigma minimum and sigma m, that is due to bending moment at that certain location. And for x is equal to 2c or x is equal to 8c, so let's see if you put the value. So now y by c ratio, if on that is top surface, then the minimum ratio between minimum and maximum will be 0. Sorry, maximum by sigma m will be 0, and whereas sigma m by minimum will be 0. But if you go along, you can see the ratio is changing, right? Now the maximum minimum, if you look at, the ratio is changing. Similarly, for x is equal to 8c, for this cantilever beam means the distance we go, that this is near to the, if you talk near to the this end, where we have maximum bending moment. So if you look at the ratio is changing, and this is where at neutral axis, the neutral axis, the maximum value of normal stress is small as compared to the this case, and so on. Now these are showing, these the trajectories are showing for the maximum and minimum principal stresses. So these lines are showing the value of maximum and minimum principal stresses, or you can say the graphical representation of these values. Okay. Now, for these type of cross section, let's suppose in this case the cross section shape result in the large value torques near the surface where sigma x is too large. For example, if you calculate the stresses at B, so for B the thickness is very small, so we have a and this distance is very small. So sigma due to bending moment will have large value, and also the tau xy will also have a large value because of the thickness. Thickness is small over here, and we are calculating VQ over IT as compared to top surface, and this distance is since very small. So the formula of sigma m is equal to my over I is, this value is not changed, significantly changed with the respect to the top surface. So depending on the cross section, your maximum stresses, normal stress cannot be at the top and bottom surface. It can be in between, depending on the value of tau xy as well. Okay. So let's see. So sigma maximum may be greater than sigma m. So the maximum bending moment stress at A, so sigma max will be greater than this value of sigma m. Okay. Now let's see an example problem. A force of 16 kilonewton is applied at the end of W200 by 52 volt steel beam. So there is a force applied on the beam, 160 kilonewton, and we have a cross section is given. The cross section is W200 by 52. So neglect the fact of the fillet of the stress concentration determined by the normal stress satisfy the design specification, they be equal to or less than 150 megapascal. In sigma maximum is allowable is 150 megapascal. So is it satisfy this condition? Yes or no? Now in this case, we cannot simply say that sigma m is equal to sigma max, and mc over I, right? So we have to find what is the stresses over here as well, and then we will calculate sigma max using the formula sigma average plus radius, and then we will compare. Okay, now let's see. So first we will find what is the bending moment at section AA, then calculate normal stress at the top surface and at flange web junction. So over here. Then evaluate the shear stress at the flange web junction, calculate the principal stress at flange web junction. Okay, then we will can evaluate that it will safe or not. Okay. Now, what is the moment at that location? If 160 kilonewton multiplied by 0.375 meters, so 600 kilonewton meter, and the shear force is 160 kilonewton. Okay. Now, sigma A and B, let's see, at the we calculated at top surface sigma A. So sigma A is MA over section modulus. Section modulus we get from the Annex C of the book. So Annex C of the book for the beam. Okay. Now if we put MA over S, so that become 117 megapascal, and which is less than the required value. And if you calculate sigma B at this location using YB is equal to 90.4, so that is 102 megapascal. Now if you compare that, that is not much of the difference. Okay. Now if we calculate at sigma B, so that become 102.9 megapascal. Okay. Now if you look at the shear stress at B, obviously at A, what happened? Q will be 0 at A, so tau A will be 0 again, so that there is no shear stress at the top surface. But if we calculate at B, so what we have, tau B is equal to VA Q over IT. So Q, first moment of area, we calculated for that shaded region, 204 multiplied by 12.6, that will give me the area, and the distance from the center of this shaded region to the center of the section is 96.7 millimeter. When we put the value, so we get 248.6 10 to the power minus 6 meter cube. Now, shear stress is equal to VQ over IT, V 160 kilonewton. We have Q, called calculator I from the appendix C, and thickness of the that portion or the web is 0.079 millimeter. So tau B is 95.5 megapascal. Now we have to calculate what is the maximum shear stress. So sigma max is sigma average plus sigma is radius, and sigma average is equal to sigma x plus sigma y divided by 2, and the radius is equal to sigma x minus sigma y divided by 2 square plus tau xy square, right? So since if you look at, let's suppose this is my x-axis and this is my y-axis, so if I represent what is the stress on that element at point B, so sigma B is sigma x, so that will become 1 by 2 sigma B, because sigma y is 0, third principal stress is 0, so sigma x is equal to sigma B, tau xy will be equal to tau B, and whereas sigma y is equal to 0. Okay. Now, if we put the value, so what is happening? So the maximum normal stress in this case is 169.9 megapascal. Okay, whereas at the top surface, so tau A was 115 megapascal. So that was within the limit. But when we find out what the maximum normal stress at the junction of flange and web, so that is 169.9 megapascal, which is greater than 150 megapascal. So the design specification is not satisfied, means it cannot sustain the load, and we have to either change the cross section or change the loading condition. Okay, now if you're analyzing the beam structure, so you have to consider where you for designing purpose where you have maximum principal stresses, and the maximum shear stress will also over there. It means if you're talking about uh, the if you're talking about the ductile material, in that case you are interested what is a maximum shear stress. So again, the maximum shear stress will be radius. If we draw more circle for that case, so it will be radius of that circle, and which is larger than this value, this tau B value. So it will be way larger than this value, or it can be larger at this C as well. So again, you have to analyze at different critical location where you get maximum stresses. Okay, now let's see another sample problem. Again, this is an overhanging beam with the overhanging beam supports a uniformly distributed load and a concentrated load as shown over here. Knowing that for the grade of steel, sigma allowable is 24 ksi and tau allowable is 14.5 ksi. Select the wide flange beam which should be used. So we have to select W beam for this problem, and where the sigma allowable is 24 ksi and tau allowable is 14.5 ksi. Means the maximum sigma max, not the bending stresses, that is sigma max principal stress, is sigma allowable, and the maximum shear stress is tau allowable, and we have to design according to that. Okay, first we will determine the reaction at A and D, and since we don't know where the maximum normal stress and shear stress will be there, so we have to draw shear force and bending moment diagram to identify the points where we have maximum bending moment and corresponding shear stress, and where we have shear force, and where we have maximum shear force and corresponding bending moment. So we have to consider both the cases, both the location. So determine the maximum shear and bending moment from the shear and bending moment diagram. Then we will calculate the required section modulus, select the appropriate beam section. Find the maximum normal stress, and we will find the maximum shearing stress, and we will compare it. Okay, first we have to find the reaction. So using the free body diagram, so R at A is 41 kilopound and force, and at D is 59 kilopound force. Okay, then we will draw a shear force and bending moment diagram. So shear force and bending moment diagram for this problem will be as shown over here. So it will start from 41 kilopound and it will be 12.5 kilopound. It will not be constant because there's a distributed load, so there's a change in shear force at each location because the whole beam is under distributed load. And then we have from minus 7.8 from C, and then from minus 43 kilopounds, and from D starting from 16 kilopound, and it will be 0 at B. because B is of overhanging part, free end. Then the shape force bending moment diagram will be like this, and it will be one order higher than this one. And the maximum bending moment is 239 kilopound inch, and over there the maximum shear force is 12.2 kilopounds. Okay, whereas Vmax is 43 kilopound, but the bending moment is very small, that is minus 40 kilopound fit, or that will be equal to 43 multiplied by 12, so that will be roughly around 516. So if I want to write, with M is equal to 516 kilopound. Sorry, this is fit. So that is, sorry, let me remove this one. Control P, 40 kilopound fit. Okay. Now, uh, now let's see how to. So based on the maximum bending moment, uh, we found what will be the section modulus. Okay. So this will be 230. Okay. So this over here, this is a typo. So this is 2880. Okay, this will be 2880. This is in terms of kilopoundage. Okay, now based on that, the section modulus is this is from Annex C. So we have 24 by 68, 21 by 62 different designation, and the section modulus is above the calculated one. And we will select beam. So in this case, we selected this beam because the section modulus as well as the area will be small. So we will select the optimized solution. So why we are selecting this one? Because of the area as well. So you can check. So it is a minimum cross section area as compared to the other beams. And now we selected the cross section, but either it will be the stresses will be acceptable or not. Let's. Okay, now we have calculated the section modulus, and we identify that this is our beam. So we selected the beam W21 by 62 with a section modulus of 127, and these are the cross-sectional properties of the beam. Now we have to verify that either this beam will support the required allowable stresses or not. Now, for the tau max, that is, we have 14.5 KSI, allowable was 14.5 KSI, and we will calculate. So the maximum shear stress of the system is minus 43 kilopounds, and the maximum shear stress will be at the centroid of the section or neutral axis. And for tau max, for W beam or IS beam, that is equal to V max by area of web. As you know, in chapter 6 we discussed that maximum shear stress in case of S or W beam, that is equal to V max by area of the web. Okay. Now, why we are not calculating? So the value of bending moment is very small. Now if you look at the value of bending moment, so maximum bending moment is on the system is mx, but at 43 kilopound, this is 40 kilopound per fit, and that's why uh, we are not considering the bending stresses at that location. Okay, now how about maximum normal stress? For the maximum normal stress, let's consider location at A, and we will calculate the maximum bending stresses at point where we have maximum bending moment, that is equal to 239.4 kilopound fit, and when we convert it, so that become multiply by 12, 287 2873 kilopound inch. So at A, max by S, so that become 22.6 ksi. Okay, now, and if you look at B, that become 21.3 ksi. But at tau A will be 0 because it's the top surface, whereas tau B will not be equal to 0. Okay, so now tau B is 1.45 kilopound per square inch. Now maximum shear stress, if you calculate, and obviously that was the allowable was sigma allowable was 24 ksi. So sigma allowable was 24 ksi. Now if you look at the value is tau B is equal to V over area of web. Okay, this should not be area of the web. Okay, tau B is not calculated right over here, so tau B should be VQ over IT. Okay, so the value is will be 1.45 ksi. Okay, but it will be VQ over IT, and over here that V multiplied by Q till B I divided by T. Okay, when we put that will become 1.45 ksi. Now if I consider the element, so we know that sigma max is equal to sigma average plus radius, where sigma average is sigma x plus sigma y divided by 2, and radius is sigma x minus sigma y divided by 2 square plus tau xy square under root. Okay, now over here sigma x is minus that is 23 tau xy, and sigma y let's take is 0. So when we put the value, so that will become this will be opposite direction, so that will become 21.4 ksi, which is less than 24 ksi. So this beam design is okay. So this we will wind up this topic, and we will discuss design of shaft in next topic, inshallah.